All right, so good day, one and all. Yeah, so this video is the final part of aromatic compound as taught by Prof. Cancer. This video will focus on nucleophilic aromatic substitution, a material being done by the GPAC Academic Board. And as a point of caution, this video is a supplementary material, not an alternative material. Very important to note. Good. So all this while we're talking about electrophilic aromatic substitution. But then we did mention that aromatic compounds will undergo both electrophilic aromatic substitution and nucleophilic aromatic substitution. So it's a 10 of nucleophilic. Now there's a first point which will bring a lot of ease to us. That is, aromatic compound usually undergo electrophilic substitution reaction. And so that forms a lot of slides, but then nucleophilic reaction is just some few things that we have to touch on. Very important. Now, second point, we are seeing that aryl halides with electron withdrawing substituent at O2 and para positions can undergo nucleophilic aromatic substitution reaction. Now, this criteria is very important. The normal nucleophilic reactions that we have, you need to meet this condition before you can undergo a reaction. That is, you should be an aryl halide. Aryl halide is a benzene ring. That is the most common example I can get. A benzene ring with a halogen on it. Very simple, aryl halide. Now, that is not the only criteria. The aryl halide should have an electron withdrawing substituent. Now, these two are not the only criteria. The last one is that the electron withdrawing group should be at the auto or para position. Very important. Now, you have to meet all these conditions before you can undergo a normal nucleophilic reaction. So we need an aryl halide with an electron withdrawing substance, which I have thought about so many already. We have so many examples already, right? And it should be at the O2 or para position for this reaction to occur. Now we are seeing in this reaction, the nucleophile substitutes the halide. And so at the end of the reaction, as has been shown here, you realize that the chlorine is no more there, and then the nucleophile coming in has replaced where the chlorine is. So it's a substitution reaction. This time around, we are not removing the hydrogen, we are removing the halogen. Very important. Now, I think it is worthwhile explaining the nucleophile here. So a nucleophile. Now, two words, nucleo, that's the nucleus, positively charged, right? And phile, love for something, so philic, affinity for something, two words. Now, this word by the root words will mean a species that will have a positive charge. Now, if a species will have a positive charge, it means that species is negatively charged. And so when we talk about a nucleophile, we are talking about negatively charged species. Very simple, right? Good. Now, if the species coming to attack the benzene ring is negatively charged, it means that benzene should assume a form of positive charge. Very important, so that it can be attacked. And that is the significance of what we have in the halogen. The halogen, because of its electronegativity, can induce some level of partial positive, right, on this carbon, so that it can be attacked. So let me show the point I'm talking about on this carbon, so that it can be attacked by the nucleophile. Now, once the attack is initiated, the intermediate is stabilized by the electron withdrawing group. And so we need these two things to be there. The first thing is that the chlorine here is creating, because of its electronegativity, is creating something like a dipole. So partial negative, partial positive. Now, this partial positive will give the nucleophile, which is negatively charged, the confidence to come and attack this carbon. Now, when it attacks it, the intermediate formed is stabilized by the electron withdrawing group, and it can only be stabilized if it's in the O2 or para position. If it occurs in the meta position, it cannot stabilize the intermediate and hence will not form. That is why we need this criteria to be met. Very important. Let's move on. Good. So we have other scenario, other cases where we wouldn't have anything feasible occurring. The first instance is when you have just bromophenol and then you add the OH minus, the nucleophile cannot remove the bromine. It wouldn't happen. But then if it happens that it is a cyclo, so this is cyclohexene, so bromo cyclohexene, very simple, right? Now this one, it can happen. This is not a benzene ring, so it can happen. But if it's a benzene ring, it would not happen. Good. That means only the halogen will not work. Now we are saying that typical nucleophilic aromatic substitution has oxygen, nitrogen, or cyanide nucleophile. So usually the nucleophile coming in will have oxygen as the OH has nitrogen as in case when we are bringing something like, so this is another one worth noting. Oxygen will probably be in the form of OH minus, nitrogen will be NH2 minus, and then cyanide CN minus. So these are the most common forms that you would see, right? The nucleophiles coming. And they are all negatively charged, worth noting. The next one is that they are saying the aromatic compound should be an aryl halide, that it should have a halogen. The halogen here is a very good leaving group. So after the intermediate has been formed, it can leave, right? It can leave. So a very good leaving group. Good. Now we are saying that an electron withdrawing group auto or prior to the leaving group should be present. Example, nitro, carbonyl, nitro, in order to stabilize the anion intermediate through resonance. So always an intermediate is an anion, and it is stabilized by the electron withdrawing group through resonance at the auto and para position. Very important. The mechanism. Now, it is interesting to note that the mechanism for nucleophilic reaction is two steps, just as we have for electrophilic reaction. The first step, interestingly, is also addition, right? And the next step is elimination. So you realize there are a lot of similarities between these two processes, and there are also differences worth noting between these two processes. Good. Now we are seeing the reaction mechanism involves addition and elimination. The first step, the nucleophile adds to the electron deficient aryl halide to form a resonance stabilized carbanion intermediate, what we call the Mesenheimer complex. So very simple, this is just a name. But now let's move on. So we are saying that this step is the redetermining step. That's the step forming the intermediate, the anion intermediate is the redetermining step, right? The second step is the elimination of the halide, right? So the mechanism has been explained to give us better understanding. Very simple. Now, what do we have here? So we have the amine group, the nitrogen, the lone pair, attacking this carbon. Now, I said it can attack it because it's partial positive, because the fluorine is more electronegative. Now, when it attacks it, because this carbon is forming a new bond, the bond here will break. Now, it will break onto the carbon of the substituent. So, this bond shared between this one and this carbon, it will break so that the new bond will be shared between this carbon and this carbon. And then because this carbon is also forming a new bond, the double bond, the pi bond will also break onto the oxygen. So the negative will be here. And so if you monitor it, we'll realize that the negative coming in is being stabilized by this. And then the next elimination step is quite like a reversal. So the negative will come back to this. The electron here will come back to this original carbon. This bond will break back onto this carbon. And then the fluorine will leave, a good leaving group will leave on its own. And that will give us the product. Two steps. Very simple. Specific example. So this is in para position. Now we have OH coming in. It will attack at the carbon bearing the halogen. Now when it attacks the bond, because this carbon is forming a new bond, this bond will break onto the next carbon, and then a new bond will be formed. And then because this carbon is also forming a new bond, the bond will break onto the substituent, the nitrogen here. Because the nitrogen is forming a new bond, this bond will also break, the bond between the nitrogen and oxygen will break onto the oxygen. That's a way of stabilizing it. Now, in the next step, there's a reversal. So the negative will come back. This bond will break back to where it was. This will break back, and the fluorine will leave. The fluorine will leave, a very good leaving group, and then we'll have our product. Two steps. Very important. Now, it is also worthwhile saying that we should be practicing this mechanism so that we can get it on our finger. It's very important noting. Good. Now, what if the substituent is on a meta position, right? Now, what happens is that upon this substitution, the electrons will break onto this carbon. Well, when the electrons break onto this carbon, there is no way, right, this would form because it's highly unstable. It's so highly unstable, and there's no substitution here to help stabilize it. And so it will not form at all, right? It will not form at all because the anion is very unstable, and then it has no substituent to stabilize it. This one will not form. So we don't want meta. We want the electron withdrawing group to be what? To be at the O2 or para position. Very important. Now, we are also seeing that two activating electron withdrawing groups provide a better stabilized carbon anion intermediate than one. So if you have two of them, let's say one at O2, one at para, it is better than just having one at either side. It's very important. Now we are saying that double nitration of chlorobenzene followed by a reaction with hydrazine provides 2,4-dinitrophenyl hydrazine. So we have initial double nitration, and when we do the double nitration, then we can add our hydrazine to get the 2,4-diphenyl hydrazine, right? Good. Now the mechanism in play. So we have our double nitration here. Now what happens is that when the nucleophile attacks, right, the bond breaks. So this carbon, the bond will break onto this one, right? Now, because this is forming a new bond, this bond will also break onto the nitrogen here, right? And the nitrogen one will break. So it will be first stabilized by the para substituent. Now, the next stage, that's the intermediate, there's a reversal here. So the reversal is the negative on this oxygen will break onto this nitrogen. Now, the bond between the carbon and nitrogen here will break back to where it was. So it's like a reversal. Now, when this one is breaking, it will break onto another substituent because the substituent here to stabilize, right? So it will break onto the nitrogen. Nitrogen, the pi bond between the nitrogen and oxygen will also break onto the oxygen, right? And that will provide the first resonance structure. You realize that in the former ones, there was just one stabilization, right? Now we have two different ways of stabilization. And we said the more the resonance structure, the more stable the intermediate and the more the product will be formed, right? Good. So the stabilization between these two resonance structures, and that will make double nitration better than mononitration on any day, or that will make two activating electron withdrawing group better than just having one of them, right? Good. And then finally, we can just have a reversal from here. So a reversal from here, reversal coming back, and then the chlorine will leave to form our final product. Very simple. There's a question here for us to try our hands on. The question is saying that we should write out the mechanism for the formation of compound A from 4-chloro-1-nitrophenol. This compound, the name is quite questionable. I'm sure Prof would say it in class. 4-chloro-1-nitro. If it's 1-nitro, we can't have phenol because if you make a phenol, it means the OH is the first substituent you are numbering, right? So it can be maybe 2 or something. But then per the diagram here, per the structure here, it means the actual name for this compound that was supposed to be typed here will be 4-chloro-1-nitrobenzene. So 4-chloro-1-nitrobenzene, that is this one, right? 4-chloro-1-nitrobenzene. So that is what we will use. Good. Now we have the next reactant being piperidine, right? So we are just supposed to show the mechanism. But now they are giving us the overall reaction. We have to draw out the mechanism. So let's share a white screen and quickly kill this question. Very simple. Good. So yes, we have the reactant, sorry. 93. So chlorine here, and then we have nitro here. Now let me draw the nitro because we are talking about mechanism. So nitro single bond ox plus, and then good. Now what is the nucleophile coming in? It's piperidine, 6-membered ring. No. So piperidine, 6-membered ring. So sorry, the diagram is not nice. Good. So 6-membered ring. So it would use its lone pair. It will attack. So the attack will be initiated to this carbon. Now, when the attack is initiated like that, what will happen in the compound? This bond will break onto this one. Now, this bond here will break onto the nitrogen. The bond between the nitrogen and oxygen will break onto the oxygen. So in the first step, the mechanism is just 2 steps. In the first step, I'll have something like this. Okay, so the skeleton of benzene. Now there's chlorine here, and then on this side, we have something like this. Good, so we have something like this. This bond will be here, and then this bond will still be here. And I'll have my nitrogen, then I'll have oxygen minus, plus. Good. So what has happened here is that the bond has broken onto the oxygen. Now, when it breaks onto the oxygen will assume a negative charge. That's what has happened here. All the other part of the compound. Okay, there's also a double bond here because this bond broke onto this one, this nitrogen. Right, this bond broke onto the nitrogen. So this is what we'll have as the intermediate. Now, in the next step, what will happen here is this, that there will be reversal. So as I always see, this negative will break back onto this one. The pi bond here will break back onto this carbon. This will break back here, and then this one will leave. The good leaving group will leave on its own. So then I'll have my final product, which will be like this. So that is it. So this will be my final product, right? So this is the whole mechanism that we have to show. We have to make sure we know where the arrows are moving from to where they are going to. Very important. And the arrows are always pointing from electrons to atoms. So it shows where electrons are moving to the atoms they are landing on. Very important, right? So this is the mechanism. Let's go back to the slide and continue. Good. So the next thing we are talking about is diazonium compound, right? So now we are saying diazonium compound as versatile starting material for nucleophilic aromatic substitution reaction, right? So we form diazonium salts, diazonium compound, and then they are versatile starting material. They can be used to produce a lot of compound, different compounds that we can't even mention. Right, now we are saying diazonium compound produce nitrogen. So that is the secret. They produce nitrogen gas. And the nitrogen gas there is a very good living group. It's actually the best living group we know. And so that nitrogen gas can leave and create a positive charge, on what? On the benzene. And that will expose it to easy attack by a nucleophile. That's a negative species. So they produce nitrogen gas as a living group. Sometimes activating groups are not even required as for nucleophilic substitution to take place. So you don't even need any activating group, right? Now the reaction follows SN1. That means there's a carbocation formed, SN1 reaction. No two ways about that. So this is the diazonium salt. It has the N2, that is the good living group nitrogen gas. It leaves, creates a positive charge there, right? Now when you create a positive charge there, in the presence of water, we can form phenol. So this is how phenol is formed. When we're talking about phenol, we said that it is better formed with diazonium salt. And then if you have your diazonium salt, the only thing you need is heat and water. So after getting your diazonium salt, you need heat and water to form phenol. Let's note this one. After forming your diazonium salt, you need heat and water to form your phenol, right? Very important. Now we are saying that iodine can be added to benzene to the diazonium salt as Ki, right? To prepare iodobenzene. So if I want to introduce iodine on the benzene ring, I can add it to the diazonium salt as Ki, and then I'll introduce my iodine. Now, if you want to introduce chlorine, bromine, or cyanide, you add it as copper 1 salt. So for chlorine, CuCl, copper 1 salt, bromine, CuBr, copper 1 salt. If you are talking about cyanide, CuCN, copper 1 salt. Now, when you add these to the diazonium salt, you can produce the corresponding chlorobenzene, bromobenzene, and then cyanobenzene. Very simple, right? Or nitro, something, cyano or nitro. So, now, this question, show how benzene can be transformed to benzylamine. Now, this one will help us because all this while the question would be how to form your diazonium salt in the first place. How do we form our diazonium salt? And this one will help us. So let's share our screen and then quickly solve this question. Good. So we are forming benzylamine. We have to know the structure of benzylamine so that we can look at it whilst. So this is it, CH2 and 2. So this is benzylamine, right? Benzyl imine. Benzyl imine. So, up to here, the whole of this place up to here is a benzyl group. This is an amino group. So benzyl imine, benzylamine, right? Now, yeah, so the first thing we do is we try and form our diazonium salt, right? Good. So diazonium salt, how would we go about it? The first thing is that we put a chlorine there or a bromine there. So any of the reactive species there. Okay, so that's a different way of doing it. Or we can decide to put a nitro group there, convert our nitro group to aniline, right? Now, when we convert it to aniline, we can change our aniline to the diazonium salt. So let's use that means instead. So something like this, we need HNO3 and H2SO4, right? To put our nitro group on the benzene ring. Now, after getting the nitro, we have to use this to reduce it to aniline. Now, after reducing it to aniline like this, we can then use our nano 2 in HCl. If you want to show him that you know what you are doing, you can put the 0 degrees there because the compound we are forming is highly unstable, and then if the temperature is high, it will decompose, right? And then we get our diazonium salt. So we get our diazonium salt. So, right. Good. Now, after getting our diazonium salt, we can add CuCN. So CuCN will give us something like this. That will help us put the nitro group there. And then we can reduce the nitro with excess hydrogen, right? In the presence of PD. So 2 moles of hydrogen can help us to get our benzylamine. My benzene ring doesn't look benzene-like. Forgive me. Okay, let me clean it and draw it well. So I'm getting something like CH2 and H2. So that is it. So this is my benzylamine. I'm done. Now, this might be confusing, but then realize that the CN is C3. So this is alkynes. This is just alkynes, right? So you can treat it as alkynes, even though it's not an alkyne. But then C3 bond N, right? So you can use 2 moles of hydrogen to break it, and then you get your benzylamine. Very simple. Benzylamine, very simple. Good. Let's go back to the slide and finish up. Now, so this is what we just did, how we have gone through all the steps. Now, the next one, benzyne mechanism. Benzyne mechanism. Now, benzyne mechanism is like RIP. I mean, on a normal day, that is what you compare it to. It is forceful. Among so many examples, just put this in your head, it will make it very simple for you. And so there are so many things that will not occur on a normal day. But then in this instance, we are subjecting it to very vigorous. Now, we are not saying vigorous. Take care. We are saying very vigorous. Good. Now, when you expose the compound to very vigorous condition, then nucleophilic substitution becomes possible. So we are saying under normal circumstances, displacement of halide, example bromide, from halobenzene is not feasible. But under very vigorous condition, the nucleophilic substitution reaction becomes possible. So RIP. Sorry. The reaction occurs through the benzyme mechanism. So we form an intermediate called the benzyne. Even though we are talking about a nucleophilic reaction, it is super interesting to note that the benzyme here is an electrophile. And then it makes sense because always a nucleophile is supposed to attack an electrophile. For instance, when we have NaOH and bromobenzene fused together. Now, if you talk about them being fused, it means we melt them together. So we're not talking about aqueous solution. That's why we're talking about very rigorous condition. We melt them at very high temperature. Now, when you do this, you produce phenol. So what happens is that the bromine will be removed and the OH will be substituted. That is very rigorous, right? Or when you have bromobenzene and you react with sodamide, sodium imide in ammonia, very powerful base, sodium imide in ammonia. Good, then you can produce your aniline. So these are mechanisms, or sorry, the equations to show what is happening if you put it in fused ammonia. Fused sodium hydroxide, or if you have sodamide in liquid ammonia, can get this. Good. Now the mechanism. We are saying all nucleophiles that react with aryl halide through benzyme mechanism are very basic condition. So the two things we talked about here, they are both bases. You should know NaOH and then sodamide are bases. But now we are saying that a proton auto to the leaving halide group, which is relatively acidic, is removed. And so what happens here is that if this is where the substitution occurs, right? Because of inductive effect, this carbon is quite positive. Now, the positivity is transmitted to this carbon, and then it's transmitted to the hydrogen on that carbon. Inductive effect is transmitted in sigma bonds, right? So it's transmitted to this hydrogen a little bit. So this hydrogen is a little, very, 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 very small. It's a little acidic. Now, if you get a very strong base, it can remove. So that is the mechanism we are talking about. It can remove this hydrogen. Once this hydrogen is removed, in an attempt to stabilize the compound, the electrons here. So the base will remove the hydrogen as a proton, right? The electrons deposited here, let me change the ink. The electrons deposited here will be contributed here. Now they are going here because this place is partial positive. The negative will want to attack that place. Now when that happens, the good living group will go away. It will go away. So when it goes away, then we form our benzyme intermediate. The benzyme is just the benzene ring having triple bond and where the double bond was. So a triple bond, benzyme intermediate. Now the benzyme intermediate is a very good nucleophile. I'm sorry, electrophile. So it will be attacked by a nucleophile. Let's go through the mechanism. Let me read the last point here. They are saying that the formation of benzyme intermediate from the carboanion intermediate leads to elimination of the halide, right? Good. So let's talk more. Yes, we are here. We are here. So they are saying that the benzyne intermediate is electrophilic and can be attacked by a nucleophile to yield a desired product. Other strong bases can be used. So we don't only use sodamide, we can use potassium tetbutoxide. potassium tetrabutoxide. Very, very strong. A very strong base. Good. So let's look at what is happening. Now, the base is removing the hydrogen. I have explained that this hydrogen, because of inductive effect, is a little acidic. So you need a very strong base to remove it. Now, when that is removed, the electrons are deposited on this carbon, right? And then because electrons are very unstable, being localized on the carbon, it will try and then move. The best point of movement is towards the carbon that has the halogen, because it has a partial positive. So it is donated there, and then, so let me start writing here. So it is donated there, right? Good. So it is donated there. It's donated here. Now, because it's partial positive here, and that will make the halogen go away. Very simple. Good. So we have this benzene form. So this is the benzene, the electrophile. Now, this electrophile can be attacked by a nucleophile. Nucleophile is a negatively charged species, right? Can be attacked by a nucleophile. So when the attack occurs, this triple bond will break onto this, right? And then the negative charge here can come and take hydrogen from ammonia. So you realize we are using sodamide in the presence of ammonia. This hydrogen, sorry, this electron here can come and take hydrogen from ammonia. When it takes hydrogen from ammonia, we come and form our aniline. Very simple. Very simple. Good. So we are saying the benzene mechanism is one route that can be utilized to introduce a substituent at the meta position of a benzene ring, already having an activating substituent like methoxide group. So this is the methoxy group, sorry. Now, the last point here is worth noting. That is why it has the nota bene sign, right? Good. We are saying that when you have an activating group on a benzene ring, the activating group will direct incoming substituent to the auto para direction. But then if you desire to put the substituent at the meta position, then you have to use the benzene mechanism. It is one of the routes. So let's look at what is happening here in the slide. Good. Now we have the methoxide. So the methoxy group. We put a chlorine on it. So we chlorinate it. Obviously, the chlorine will be directed to the auto or para. Now it has been directed towards the both angles, but then what we are interested in, we just choose one of them. So the auto. Right? That's not what we are interested in. Now we want to put amino group on it. We want to put the amino group at the meta position. And so what will happen here is that, let me try and explain it here. What will happen here is that this is the hydrogen we'll be interested in. This hydrogen here, right, will be removed. A benzene will be formed between this carbon and this carbon. This chlorine will go away, right? Now, what happens such that we'll form two products, even though we have written one of them there, right? We have two products because the benzene can be attacked from up there or down, right? The benzene can be attacked from up there. So if I'm supposed to explain this in details, what will happen here is that between this and this, I'm sure we can figure out that we are forming, yes, we are forming something like this one. So this is it. So the benzene can be attacked. So the amino group coming here can attack from either the up there or down there. So it can attack from here or here. Right. Now, if it attacks from up there, we are getting an auto product. So we get something like this. Right. If it attacks from this side, we'll get this product. Now, because this is specifically to explain meta substitution, that's why we have isolated it. It's just like bringing one product from this, even though there are two products. Right. So very simple. If in exams we ask you to produce something specific, don't worry yourself with all the side products. You can just go ahead and then focus on the main product. So that's what has been illustrated here. So the first one, chlorination, we choose the auto product, and the next one, that is we exposing it to fibrous condition. Even though we should get two things, auto and then meta, we are just focusing on what the meta product. Very simple, right? Good. Now we have been blessed with one last example to exercise. That is, what products will be formed when p-bromophenol reacts with sodamide in liquid ammonia? Now, what will show that this is a benzyme thing is because of the vigorous condition that we have exposed this one to. And then what we have talked about, I'm sure you would be realizing that we'll have like two products formed here. Two products. So we have a meta product and then we'll have a para product formed. Let me use the white screen to finish this whole discussion. And this is the last. Okay, so white. Okay, so that's the last question. White sheet, bromophenol. Good. Okay. So bromophenol. Bromophenol. Right. Now what will happen here? Okay, let me not use the resonance hybrid because I'm coming to show mechanisms. 1, 2, 3. Good. So I'll have this. So the condition sodamide and then liquid ammonia, NH3. Right. So I'll have this. I will have this. One product. So one of my products will be here, NH2 here, plus another product. OH, a para product, so NH2. Right. So these are my two products, right? Good. Now, there was another question I didn't look at. Let me go and look at it quickly. So they're like, we should provide the mechanism, right? Provide the mechanism. So let's just work around this. Good. So my bromophenol, let me draw it again. Attempt to provide the mechanism. Attempt to provide the mechanism. Good. So this is, oh God, bromine. Let me change the diagram. So let me change the whole of this. Sorry for my diagram. Very bad. OH. So double bond, double bond, double bond. Good. So what will happen here is that one hydrogen here would be attacked, right? Now that hydrogen will be attacked by the amine group here. So the hydrogen will be attracted as a proton. This bond will break onto the bromine, right? Onto the carbon within the bromine. So what we'll have here is this. Okay. So let me take it step by step. So the first one is just we having good. The first one is just we removing the proton. Just we removing the proton. Sorry. So we have something like this. Okay. The Br2 here substituted. Now there will be electrons deposited here, 2 electrons. The double bond is still intact. All the double bonds are intact. Good. So that is the first step. The next step is, now this is very unstable. So the electron will try and attack the carbon here because it's partially positive, right? And then that will see to the removal of this bromine. Let me separate the bromine a little bit. So that will see to the removal of this bromine. Let me see. That will see to the removal of this bromine. So it's attacking this carbon, then the bromine will leave with the bond here. So I'll have something like this. And that is what we call the benzyne intermediate. The benzyne intermediate. So OH here, C, triple bond C here, double bond, double bond. Now, the benzyne can be attacked from two angles. It can be attacked from two angles. So it can be attacked from here, that's the para end. it can also be attacked from here. So assuming this one is A and this one is B, if it's attacked via the A area, we are getting something like this. So this is A. So we are getting something like this. The NH2 will be here, the OH will be here, and then double bond, double bond, double bond. The electrons will be back here, right? Now, if it's attacked by the B, then we'll have this. The OH will be here, then the NH2 will be here. Good. Then we'll have the electrons being deposited here, double bond, double bond, double bond. Good. Then from here, we would have the ammonia coming in, right? So the lone pairs will take hydrogen from ammonia, right? So that the bond between the nitrogen and hydrogen will break onto the nitrogen. Good. In this place, it's the same thing. To the lone pair, ammonia, H2. So the lone pairs here will come and take hydrogen, just the proton from ammonia. The bond here will break onto this. So in the first instance, the first product we are forming is this para-aminophenol. Para-aminophenol to para-aminophenol. So 1, 2, 3, NH2, OH. That's it. Then the next instance, we are forming meta-aminophenol. So it will be this. OH, NH2, 1, 2, 3. So that will be that for that question. The diagrams are not nice, but bear with us. So that will be all for aromatic compound discussion. Yes, as I always say, this is a material being done by GPSC, University Academic Board. And if you have any questions or if you want any clarification, kindly see any member of the GPSC Academic Board. Thank you very much for staying with us and all the best.